happy to see you here, all the brave people listening again about security. It's been like, there's many talks, in fact, like about security, which like, I'm an AppSec engineer, I'm kind of happy seeing like security becoming a more widespread topic in software conferences. So we've heard this morning with Cameron, like how great Go is, especially from a security point of view and all that. This is true, but we'll try to see by sharing like in full transparency, in really with tiny details, like you're not totally immune to security issues if you're using Go, and we will share like 2 lessons about nasty vulnerabilities that happened at Grafana Labs, and also what can we use from the Go ecosystem and all that to make sure you don't fall in the same traps. So, security engineer, Grafana Lab used to be a backend developer like almost a decade ago. I had to use Java at that time, that's life. Yeah. Well, things can only get better. So, we will see how, like, yeah, in general, that's true, like, Go is secure, but sometimes there are, like, gray areas, like, where you can have some confusion, and security-wise, you'll see that vulnerabilities happen when there is confusion, because it means, like, somehow your software will start doing unexpected things, and if someone ill-intended starts to say, hey, now if those unexpected things are bad things, like what can happen? So we will see 2 vulnerabilities, one from end of 2021, which was scored as high, and we will see why 5pass.clean, Matos fail. That's interesting that Cameron this morning introduced Go fuzzing. You will see like how it's useful in practice to get coverage on that topic. And then we switch to a critical vulnerability that was discovered internally, where it will be about concurrency, memory management, the ugly part of it, like if we talk about the keynote yesterday. And now we use load testing with a tool that we are developing at Grafana Labs to prove that it was bad and also to convince ourselves that now it was fixed properly. So, yeah, won't speak more. According to go.dev, like simple, secure, like scalable system with Go, like it's memory safe, statically typed, which makes it like, as a security engineer, it makes your life far more easier because you don't have to handle memory, so no like C errors like buffer overflows and all that. And it's statically typed, which is also a really nice security property, which means that it's super hard to have, when something is statically typed, to get remote code execution, because it's going like, let's say like if you have a list and you have a dynamic language, somehow those objects could be transformed into like functions. And then from functions you can execute evil code. And why it's statically typed? Well, you can't like get out of track basically. So that's good. And also something like golang check, gosec and all that, it's really super good at spotting like not security issues, but let's say bad practices that could lead you towards like security errors. Yet with all that, we had several vulnerabilities because of unexpected behavior. And I say that, like, to be honest, if you look at the doc and all that, well, in fact, it's expected. But as a developer, if you use it, if you use like those features, you are not totally expecting this behavior, and this is clearly the root cause. So back to December 2021. So you will see, this is a security talk. Like many security talk about vulnerabilities, they don't want to share details because people are afraid and all that. We're an open source company and all that. We like to share. Go is an open source language and all that. So I'll make sure to share the slide afterward. All the links you see there, you can click them. You have full details, GitHub, PRs, comments, issues, whatever. So what happened? December 2021, a security researcher found a path traversal. What's a path traversal? Basically, let's say you have a feature with a file name as parameter, and someone starts giving, like, instead of giving just like filename.pdf, starts giving you dot dot slash dot dot slash etc, like password or whatever. And this security researcher, he was rather young, and he was super proud to have found that. And he said on Twitter, "Hey, that's amazing! I found a path traversal on Grafana." But of course, he didn't give all the details. But it only took a few hours to the other, let's say, security researchers, like the one where they put the hoodie on, to say, "Hey, well, now there's something to hunt for. That's easy. We're sure there is a path traversal. So now let's start using it." And so after a few days, like on December 7th, we realized that it was already actively exploited on our cloud like instances and all that, making it officially a 0-day, meaning that it's exploited. And you'd never know if it's like on target, like you really to steal things or just to test. Well, anyhow, the fix was in the loop and it was released on this day. But then the question like we should ask ourselves is like, how come this happened with the Go standard library, like supposed to be secure and all that? It kind of look as a, like, you know, basic mistake and all that. And Grafana software has been there for years, so how come like it was not like identified before and all that? Well, we'll see that filepath.clean is confusing. If you just read the doc super quickly, one line says, yeah, it says like it returns the shortest path name equivalent to path, which sounds like exactly what you would like to do when you are trying to get rid of path traversal. You give it the user input with dot dot slash whatever you want and all that. And if you just read this line, you suppose that as a result, you will get the canonical path, the simple version, which should be clean, because it's called cleaned. Please don't go through the details if you want to waste your time. Like, just read this doc later on. It's so long that you read it, like you're not even sure what it does. So what I do when it's like that, I just go to the Go playground, like simple example there. First, like I try to make a summary of what I understood it does. Well, in fact, it removes all those dot sequences for all the inner elements, and also from the first element if it starts with a slash. So what it means in practice, that it will not remove the first dot dot if it doesn't start with a slash. And we can test it, still working with latest version of Go. Of course, you know, like compatibility and all that, you cannot like break something now. So that's life. And maybe at some point, like, yeah, maybe I'll discuss more with Cameron and say, hey, can we have a safe clean or a secure clean or whatever? And you just do that, and then you realize that, yeah, well, if you put like dot dot slash data, it's not cleaned as you suppose it would be clean. So in practice, it meant like for Grafana, for example, someone could ask, instead of getting a public resources, it was asking for dot dot slash private, and you start getting like config files with secrets in them and all that. Full transparency again. Vulnerable source code is here. What we were doing, yeah, we were doing clean of the user parameter, and then we were joining that to our plugin directory. And if you read that, like it should be okay, because you have a user input, yeah, that's dangerous, but you clean it, and then you say, okay, now with this clean user input, I'm just looking into the plugin directory. And where it gets like even more interesting is, because we run GoSec, we had a warning about it, because GoSec will say, hey, you know, when you're doing like join like that, it could be dangerous and all that, but we added a comment. And we silence the rule. We say that, yeah, well, we are safe because we just cleaned it. So thank you, GoSec. But your point does not make sense in our context. And where it gets even more interesting, if you look at the definition of this GoSec warning, which is like, yeah, file path provided as tent input, like basically, okay, a user is giving a file path, this is like super dangerous, you should be careful. And in the documentation of this rule, like they say, like, hey, this is how you should fix it, the right way. Use filepath.clean. So there are, let's say, if you do your job properly and you take the time to read all the docs and all that, and you don't test like // there's no way you can like realize that this can happen. Well, the fix was easy. Well, we were in a rush, so try to make something simple and all that. Well, hey, just add a slash, and then it should be done. Yeah, and then yeah, you had some unit tests and all that. So you can see all those PRs and all that stuff from December. You can see when they were merged and all that. Maybe people working in the weekends and all. And you can also see in all those PRs like improvements and all that, like how we plan to do better things and all that. But I don't want to enter into those details. I want to discuss about like something more useful in our context. Go fuzzing, which was introduced this morning by Cameron. So the idea of fuzzing is, well, we have unit tests, but here what we want to test is not that the feature does what it should do in the normal use cases. Like basically we want to test many possible malicious inputs, and you don't have a clear definition of them. You cannot say like, hey, I'm gonna test .. / and then whatever, and then what about Unicode, and all this kind of thing. So the power of fuzzing is you try to abstract that and you try to describe things that should never happen, and then you have an engine that automatically generates random inputs and tests them against the predicates. And of course, if it finds an input that breaks the predicate, well, you have an issue, your source code is wrong, you should fix it. So it's available natively from Go 1.18. And then what's super cool is when you run it, first, like it's super quick. We'll see a few examples. And if it finds something, it creates test data file that you can just put it into your CI pipeline, and somehow they create like test files for you for those kind of nasty inputs that you want to make sure later on you test again. There's a nice tutorial, but let's see an example in practice. So okay, this one we saw it. Okay, our fix, we just put like / in front of our parameter, and normally if we do that, we clean and we put a / before. This should be like super clean. Then we want to write a fuzzing test. So the idea, and it's really nicely integrated and all that. First, like you don't need any extra tool. It's just a Go binary and all that. You define a few test cases. So those are input vectors. And in fact, they are things you want to test, and then they would be mutated, they would be changed randomly, so that they will change like one letter after another and all that. So if you're able to provide some malicious inputs, as an example, it will help the further to be quicker and to like start playing with those like strange character. Then you create your test case. In it you say, oh, okay, I call my method, and then you write your predicates. And so in this case, for example, we say that, yeah, well, when it's cleaned, we should never have something that starts with a /. No, we always want it to start with a /, otherwise it's weird. And we also want to say that, yeah, it never contains .. in the middle, because it means like cleanup didn't work. And then the only thing you have to do, so you write like, either you run it as a regular test with Go test, and it's just like test your 3 inputs, and then that's over. And if you want to start all the random generation and all that, you just have to add this extra first parameter, and then it will start running lots of threads and trying to find like inputs that break the predicates. Of course, when you write the predicates, you are wrong, because it's not obvious to write them and all that. So what happens in practice? You start fuzzing, you see results, and then you say, well, in fact, they are legit results, so I messed up with my predicate, so you like trial and error there. And sometimes it gets harder, and it's where confusion like starts to appear. You don't really know, we'll see, like if it's a valid or an invalid input. And there, fuzzing helps you decide, like, yeah, should I process this input that will give this strange output? So for example, here, if we change the predicate and instead of saying like I don't want slash dot dot slash, but I don't want slash dot dot slash, then really quickly in a few milliseconds, like Go finds an input, which is like, hey, you give that as a file name, 0 dot dot slash 0, and then as output, it gives that. Like, okay, is it a valid output? Does the input make sense and all that? Yeah, well, in fact, it's super hard to decide and all that, so it's probably like not exportable and all that, but what it means is in your function and all that, you probably want to say, hey, I don't want this kind of input, and all that. So here, the real power is forcing you to ask a question, saying, hey, what will happen if a user starts sending me like data like that? How should my software behave? And if you don't know, then you have a defensive approach, which is like, yeah, I don't like this kind of input parameter. I don't know why I should have a digit and then like dot dot or whatever. I just like remove it. So that's the nice story for fuzzing with a simple case, just a parameter and all that. Then we tested it on something a bit more complex. So we have plugins in Grafana, and we sign those plugins to make sure they are not tampered. And so we have a manifest file. And in this manifest file, we have a tree of file names and folders and all that. And we want to make sure that each and every file in the manifest corresponds to the plugin, and we do a hash for each and every file and all that, which means we need to, again, do like path processing and all that. Of course, we reuse our new self-clean version there, because we learned it the hard way and all that. So here, I extracted the source code of the method and all that. What really matters here is this case here, like, yeah, it looks strange, like here. Why are we doing that and all that? Is it enough and all that? We are trying to do like, hey, to say, we are looking for symlinks, and we say, okay, it's false, and it's super convoluted. You read it like 2 or 3 times when you do the peer review and all that. You're not sure if it will figure out if there are symmetric links, if they are well-defined and all that. So again, rather than, trying to burn your brain, trying to understand if everything has been like tested as it should and all that, yeah, let's try to fuzz it and see what the further like finds as strange outputs. And from there, you'll have a better idea if the implementation like seems to be doing what it should do. So other like inputs, you want to test it. And there, well, it gets like more difficult, because your expected result is not trivial to expand. So you want to be able to express that, hey, I don't have any symbolic links in my file manifest and all that. So somehow what you end up doing is, well, you have to re-implement by yourself the logic. So somehow you have to come up with a second implementation of what you are actually testing. And so this is where we start like seeing the limits of fuzzing, because you have an implementation A where you want to make sure it's good enough, but then you are not able to express it as a simple predicate because it's too complex, because there are corner cases and all that. So somehow what you are doing, you are naively rewriting it another way, the way that makes more sense for you, and you hope that they always match. And if they always match, then somehow it should be fine. So that's what's being tested here. But when you do that, like it's not super convincing because like both could still be wrong, but statistically it's unlikely that both are wrong always for the same input. Yeah. So here, for example, I use a simple version like, I want to know if I'm still in the best folder and if I have not followed symlinks. I'm just checking like, does it have this prefix and all that? So that's not super robust, but it should be enough. And then when you run it, that's interesting because it fails. Of course, like first time it failed because my predicates were wrong and all that. But then when the predicate seems okay, you get something like that, hey, well, in fact, this big method we saw before and all that, it fails if you give this input. It considers it's a valid input and all that, whereas it shouldn't be. So maybe there's no security vulnerability having in a file manifest a file that's called //. But you don't feel comfortable like with having it because maybe then someone can include like a base folder or whatever with it, and then the signature will be wrong and all that. So trigger the discussion. You can like see it in this PR and all that, and then we just fix it, having this use case and all that. So which means that here fuzzing has been used to help with a peer review of a validator, which is like not straightforward to write, and it helps us like discover like corner cases and all that. And now somehow we have the official implementation, a naive other implementation, and they match. So that was for the first vulnerability, and where like Go fuzzing really shines. So now another thing, like as soon as you play with slices, like you get strange things happening and all that. But we will see that it's not just bugs; it's just not nasty things. There can be like really dangerous things. So what happened? So we have a cloud version of Grafana. We update like regularly and all that. And then at a point in time, we had multiple customers like complaining, say, hey, well, we can't like sometimes we can't see our data. And then when you look at the log files and all that, there are for all three errors, like users that should have access to their dashboard. From time to time, they refuse the access, and then the second later, they can see the dashboard if they hit refresh and all that. So Grafanista found the issue, like, concurrency stuff and all that. Of course, you know, when sometimes it works and sometimes it doesn't work and all that, and you suspect it's there. Then we got that reported, okay. That's hard, the sentence is really hard. It was written like that, but we have found a shared slice write trace condition when initializing handlers for the middlewares. It's a lot of things. But what's interesting there is security team was looped in at this moment, which is like, okay, so we've seen like there are access issues and all that, so that's the case where a user complained because they can't see things they should see. But maybe the opposite of it is happening. Maybe sometimes people start seeing things they shouldn't be seeing. So let's do a security assessment. Let's see what we can do about it. So to easy understanding, so to make things super easy, in Grafana, we have API routes where we map the URL and then a business logic, and we have middlewares, which are shared code that can be called like before or after the business logic. So many of them are before for authorization and authentication purpose, like making sure user is logged in and all that. And we also have some that filter the data when it's returned, so that like depending on the permissions of the user, when the search is done, we remove everything that's not supposed to be seen by the user. So it ended up being like that, just, okay, the API route, a few middlewares, and then the method that has to be called. So why appending to slice is dangerous. So for all the details, this article is really, really nice. Takes about like 10 minutes to read in details and all that, explaining you all the gotchas and all that. But what's more important for me, like with my security hat, is this sentence that leads to unexpected program behavior, which is surprising to many developers. And it's because slices are references. And we end up like in the memory management part and all that, which means that when you play with arrays, they are passed as copies, which means that it's your version, so you can do whatever with it. It's not going to change the initial version and all that, so you cannot mess up with the data of another user because you just get a copy of your thing and all that. When you're using with slice, no, it's using references. So you could start mutating like shared data. But the TLDR of this article is like really interesting. From a memory management point of view, Go tries to be smart, and so assigning memory for arrays, like it takes time, it takes memories and all that. So what the Go compiler do is it will like reserve memory for an array for a certain size and all that. And when you're using a slice and you try to append elements to it, it will not allocate a new one. It has like some room for extra elements, which means that if you're appending to a slice, sometimes it is cloned when there is not enough memory, sometimes it is not cloned. So you could have a totally different behavior if you're adding one element or 1,000. So that's in the unexpected or unpredictable like part of it, which we'll see caused havoc. So there's a pull request like with many changes and all that, but the description like should be enough. Basically, so we can have several middlewares for each and every route, and it was decided to refactor the way it was working to make sure now that we guarantee the ordering of middlewares. Normally it shouldn't matter, but then when you start adding more and more middlewares, in fact, you are making assumption that, hey, middleware B should happen after middleware A, otherwise it doesn't make sense. Like you want to check an extra permission of a user, but if you have not like authenticated the user yet, it doesn't make sense and all that. So there's this comment which is like someone doing the peer review and all that. You say, okay, why are you doing this refactoring and all that? Well, we are changing the way it's written, and middlewares are temporarily kept in a slice to preserve ordering. A slice. So that's the thing. If you look at the details of the PR, there was no slice before, and now data structure has been introduced to try to add ordering on those middlewares and all that. To keep things short, here's a bug fix. So how we fix the issue, and then we will discuss how we could turn that into a really nasty security vulnerability. So how it was fixed. So yeah, users complain, yeah, I can't access like from time to time to dashboard. So the only thing that's done, like it seems like super simple after the fact, after a few days of hard work trying to understand what happens. And all that, yeah, well, we just make a copy of our thing, and with that now we are sure that we can't mess up with a middleware list of another user or whatever. As soon as we start like creating our HTTP context and all that, we get our list of middleware, we make a copy for us, and then it's going to be fine. Okay, so the bug is fixed. Users should be happy and all that. But what about all the users that are running a Grafana instance that is not patched? What if maybe it has been exploited and all that? So how can we exploit that? Well, if we try to sum up, like, yeah, we've seen that the slice can be shared instead of being a copy, and somehow it depends on its size. So that's an interesting thing. So in practice, it means, like, in like simple terms, that we should be able to make request A receive the list of middlewares of request B if they like happen almost at the same time. Which means that, for example, you could say, hey, so now let's suppose there is an admin like with privileges that is like looking at a dashboard, authenticated user and all that. And then at the same time, there's a malicious user that's not authenticated and all that. Maybe if the malicious user is lucky and he says, yeah, I want to see like dashboard number 1, he will see it because he will get the middleware response from the admin and all that. So to prove if this is possible, like, you start at, you have no clue if it's a really unexploitable REST condition, and it could be exploitable, but you're never able to reproduce it without like testing for thousands of years, like just like for the proper timing and all that. But yet, it's important like to try to reproduce it, just to have an idea if it's like, is it a real vulnerability, like where it's likely that someone can exploit it, or no, it's just like, it's sci-fi, yeah, maybe this could happen, but it shouldn't happen in practice. But we have to keep in mind that it happens often, rather often, so that we have users complaining because they couldn't access their dashboard and all that. So it should be possible to reproduce it. So the strategy was to say, okay, like to optimize success, we test everything locally so that we make like all these like random latency network issues disappear. And we will focus on endpoints with only one middleware because it makes things like much more easier like to reason about. And then what we want to do now with our Evil hat on, we want to maximize the impact. Like if it works, we want to see like something really bad happening. So that's probably the most sensitive endpoint on the Grafana server. So you have an endpoint where if you are the super admin, you can reset the password of anyone. And then there are like on the opposite side of the spectrum, you have public endpoints to see public dashboard. So if we mix up calls between that, maybe we can, as a non-authenticated user, we can trick the server to reset the password of anyone, which will make it like this 9.8 out of 10 score, like security score, which is like the kind of one of the worst things you can ever imagine. Like you have your server, someone starts sending like few requests, and then he changes the password of the admin, and then he's in, and that's game over. And then the other question is like, can we see it if it happened and all that, if there are tries and all that. So what can we do there? Well, we need to do load testing. And we're lucky because at Grafana Labs, we have a team that work on the tool called K6, written in Go. The engine is really good, and they are optimizing for developer experience. So making load testing easy and efficient and all that. So it was the obvious choice, and when trying to reproduce it, like first, like it's easy to get started, like docs are really good. I knew I could, if I wanted like something specific, like really pushing out the load and all that, like talk to them and have like support and then tuning and all that. And we're also interested in using this tool like in the security team, like for dog fooding. So I see people taking pictures. Please don't use it against unpatched instances. People should patch. It's been like 6 months, but so So K6. So it's a Go engine, but you write your load test. Now it's like not only load test, you can do much more testing with K6, but in this case it's a load test. You write it in JavaScript. It's not Go and all that, but sometimes you need to write also a front-end test, and yeah, you need JavaScript. Yeah, that's life. So what we are doing here, we have those two URLs, the one which is resetting the password of user one. User one is the first admin in the system. And then we have a dashboard like called something like useless dashboard and whatever. We prepare like a payload where we set the new password for this endpoint, which is just a me password. And then what we do, we prepare scenarios. So scenarios are basically like which tests you will load, you will launch. And then we say that we will launch 60 virtual users for 2 minutes for both the protected endpoint and the unprotected endpoint. So basically, for 2 minutes, you will have 60 admins, real admins. You will have 60 malicious users. You launch that, and you hope to see a collision where something happened. And there, we define the expected behavior, and you will see that it's like there are like similarities with what we were trying to achieve with fuzzing and all that. So we are writing a predicate, and we are trying to write now in the slow test like things that should not happen. So especially we want to write things that should not happen for the unprotected for the protected route. So okay, we do our put. So we try to call like reset password on user one. And of course, what we expect is that we don't get a 200 because if you see in details, we are not giving any authentication token and all that. So we are just calling publicly the reset admin password without any credentials. So of course, if we get a 200, which is successful, it sucks. And if it does, so if it doesn't, that's normal, it's added to the start, and then that's fine. And if it does, we just say, hey, well, in fact, we stop, and then we say, hey, well, password has been updated. That's the end of the world. And then the other predicates, like we don't really care. It's just like we could be like, yeah, more accurate there, but we don't really care. We say that, yeah, the public dashboard, it should always be a 200. If it gets refused, that's strange. But if you start being picky and say, yeah, if I don't have a 200, like maybe I found the vulnerability too, that's wrong because we will be having a lot of load, so you can have like 500, 400 errors and all that just because of like the server is crashing and all that. So it doesn't really make sense. And somehow we don't care. What we really care, let's say from an attacker point of view, is having set the password to dummy password. So I will try something crazy. You shouldn't do that, but I'll try. So not sure it's gonna work, but you know, Grafana is a Go server. The engine of K6 is written in Go, so it works like rather nicely. So we'll try to reproduce it. Maybe we'll need like a few tries. So right now, if you look at the Grafana server, I log in as admin and the password is admin2. No, it's not. Yeah, okay. So I'm in like that. So I'm the real admin and all that. So it's just a Docker running. Okay, I'll try to put it bigger. Can you see enough?
View make text bigger.
Yeah. Yeah. Okay, so what we're gonna do now, so we see the Grafana instance is running. So we've prepared a K6 script, the one we've seen before. We just launch it, K6 run, and then we wait. And if you're lucky, it takes a few seconds, and we are lucky. No, that's not luck. That's just because it's Go engines, so it works. So here, what has happened after a few seconds? Let's do it like that. Yeah, password has been updated, so it only took 5 seconds. Yeah, so now let's, yeah. Let's try now, because it's too easy to fake and all that. Like now you type dummy password, you see it's much longer. No, I didn't type it well. No? Yeah, I mean, so. So that's bad. So that's bad. And so that's why I was happy that it was discovered internally. Well, like, not discovered internally, because at the end of the day, it was customers complaining because they didn't have access. But with the cloud version and all that, we got feedback within the next few hours of deployment, which means that we could like react quickly, and then we have this feedback loop, and it was like, that's why I love the culture at Grafana Labs and all that. Like, people come to you when they have questions and all that, and they try just not to fix the issue, but like to have this wider view of, yeah, it could be worse, and can you help? And it sounded like not possible, like right away say you're not gonna reproduce it, but in fact, yeah. So, one last thing, we have a public bug bounty program. If you want to play with rest conditions and all that, maybe there are others, we hope not, but maybe. So, like for this kind of vulnerability, it will be like around $20,000. So, if you want to have a look, please do. So, to conclude, yeah, we've seen that filepath.clean, it's tricky when you try to protect from path traversal. It doesn't clean in all cases. We've seen that with Go fuzzing, it's rather like an efficient way to validate your, I'll call them like security validators, like any security helpers that try to get rid of dirty inputs. So it really spots quickly, super quickly, like corner cases, like a human brain cannot think about, like Unicode encoding and all this kind of thing. It will look for them. So if you want to play with fuzzing, I think you like, even like sometimes you get like a really difficult PR and all that, like fuzzing can really help you like understand like which corner cases are not handled. Well, we've seen that appending to slice is dangerous, like to be honest. Concurrent programming is dangerous. Doing concurrent programming for security purpose is extremely dangerous. Which means that if you have to do it, like, you have to be super cautious. And if you have to review a PR for something like that, be super cautious, because you read between the lines, it seems okay, but you have to have really like things about like concurrency in mind and all that. You see it's a pointer, it's doing authentication stuff, like it should like raise a red flag and think about it. And there, it's where K6 can really help you. Like, you know, you can put a comment in the PR like, yeah, maybe we have rest condition, or I'm not sure that's not, and then what should we do and all that. K6 can be super useful, like to prove if it's real or not. And then what was interesting also, like, yeah, everyone says, yeah, applause, because with this K6 script, we can hack the system. But what's more useful for me is that now with this K6 script, we run it against the patch version, and we cannot reproduce it anymore, even if we launch it like for hours. So now, it's not we have 100% confidence, but we are highly confident. Without it, we will have said, like, yeah, okay, we have a fix. It seems to work statistically, like users are not complaining anymore, but maybe we've just fixed 99.99% of the problem, but we will still have access issues and we don't see them. So there, there are two load testing tools, in fact, like go fuzzing and load testing can really help you quickly make sure you cover those things that are hard to cover, like if you just do like unit test or integration test and all that. And then I'm happy to take questions.